Hello, it's Brian again. Today we're going to be looking at correlation and some basic, or I'll call it simple linear regression in StatCrunch. So when we're talking about correlation, we're looking at a linear relationship between two variables. So when one of the variables tends to be higher, the other one either tends to be higher or tends to be lower, right? That an increase in one variable is associated with an either across the board, it's usually associated with an increase in the other variable or a decrease in the other variable. And those are referred to as a positive linear relationship and a negative linear relationship. So anyway, we're going to measure this with what's called the correlation coefficient, which is another statistic that can be calculated. Here's an example. A pediatrician wants to determine the relation that may exist between a child's head and the head circumference. The child's height and the head circumference. She randomly selects 8 children, measures their height and head circumference, and obtains the data in the table shown. So here's the table. So if the pediatrician wants to use height to predict head circumference, height is known as the predictor is also known as the explanatory variable. And the response variable is what we're trying to predict. So we're trying to predict head circumference. Head circumference is the response variable. The explanatory variable is height. All right. Now let's actually go to StatCrunch for the rest of this. Let's take our table and let's click open it in StatCrunch. All right, so we have our data here. I'm just going to briefly move it now. The first thing we want to do is to create a scatter plot of the data. Scatter plots are easily made under the graph menu. We go down to Scatterplot. Simple enough. The x variable we want to be the explanatory variable, which in this case is height. And the y variable is the response variable. That's going to be head circumference. Okay, I'm just going to click compute and see what this looks like. We may want to play with the options, but the basic scatterplot might be perfectly fine for what we're doing. This looks good. It looks like we've got our you can see the height in inches down below. We have this nice little pattern. I'm looking over at the choices. So let's just check. You see we have height on the x-axis, circumference on the y-axis. We can just double check. This looks good. We have the same units everywhere. Choice A is the correct answer. All right, we're going to compute the linear correlation coefficient. Let's go back to StatCrunch, and I'm going to close this. The correlation coefficient is easily calculatable. We don't have to deal with any formulas. We're going to go to, so we go under Summary Stats and go to Correlation. We're simply going to pick both of these, so I'm going to hold down Shift while I click both of them. Those are the two variables. Let's see. Let's display the two-sided p-value. I'm going to just click compute and see what we get. Okay, so this gives us our correlation coefficient, 0.9371. 0.937, 3 decimal places. Now, does a linear relationship exist? To answer this question, we have to ask, is this correlation strong enough for this size of a sample? We have a sample size of 8, and so we have to look at the critical values for a correlation coefficient. You can see this table. If I click that, I'm going to get this very simple table. It just says, for any given sample size, how strong does the correlation coefficient need to be in order for me to claim there is a significant correlation between the two. So it says for a sample size of 8 that I need a correlation to be either greater than 0.707 or less than negative 0.707. So this is saying in absolute value terms, the correlation coefficient must be at least this big. And it is, right? We have 0.93 and it is. So we say yes. There appears to be a positive linear association between, because R is positive, yes, and it's greater than the critical value. That's choice A. It's greater than the critical value. Okay, now we're going to look at comparing two populations and comparing their correlations side by side. So what I want to do is, so what would we have? Researchers are wondering whether the size of a person's brain was related to the individual's mental capacity. They selected a sample of 5 females and 5 males and measured their MRI counts and IQ scores. The data is reported to the right. Complete parts A through D. Okay, so first a scatter diagram treating MRI count as explanatory and IQ as a response. So let's open our data in StatCrunch, just as we did before. Now, right now, I have we have our data in 2 columns. I want to create a scatter plot with everything on it. I don't think I can do that without moving the data around. X variable, I'm going to have to, what I'm going to do is do a copy, Control X, copies, or that cuts, and then paste is Control V on a PC. On running Windows, I mean. Anyway, this is the males and the females. I'm all combined into one. I'm going to separate it out a little later, but for now, let's see what the combined scatter plot would look like. My X variable, I want to have MRI, female MRI, although it's actually not just female, it's all MRIs. And IQ is the response variable, because it says we're trying to predict IQ score based on MRI. Okay, so you can see what we have. The MRI is on the x-axis, we have IQ on the y-axis, and we have this pattern here. It looks very much like choice C. Let's get a closer look. We've got, it's very faint, but you can see the dots match up in the same places. IQ, MRI down below, everything looks good. So it's choice C. All right, compute the linear correlation coefficient between MRI count and IQ. Are MRI count and IQ linearly related? So we're going to go back to this. We're going to go to stat, summary stat, correlation, and we're going to take those two. At this point, we're not breaking the population into subpopulations of male and female. We're just looking at what is the correlation between them. Okay, it says it's 0.703. That would round up to 0.704. Is that strong enough? Let's go back here. We have a sample size of 10. This table of critical values says a sample size of 10, we need a correlation coefficient to be at least as strong as 0.632. That is strong enough. 0.703 is bigger, so I'm going to say yes, we are linearly correlated, but remember I'm going to have to round up 0.704, and now we're going to see how this breaks down between the males and females. So I'm going to in order to get a scatter plot with the different colors, I have to do a little bit of manipulating of the data. So what I'm going to say is have sex in the in this other column, and I'll have F, 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 F for the first 5, and then M, 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 M. Let's fix that. M. Okay. Let's just call this MRI. And let's just call this column IQ. So what I'm going to do when I graph this now, graph a scatter plot, I'm going to still select MRI to be on the x-axis, IQ to be on the y-axis, but I'm going to group by sex. And when I do that, I have grouping options. I'm going to color the points by group label. What that's going to mean is that I'm going to get all of the female points are going to be in one color, male points in another. Right now, I don't know what colors it's going to use by default, but that's fine. We'll just let it go and see what it comes up with. It'll pick two different colors. It'll tell me what they are. So you can see what we got. We've got the blue for the female and the red for the male. So it looks like from this data set, the males tend to have higher MRI scores and higher IQs. Females have lower MRI scores and lower IQs. But this is just data that was made up for this problem, right? So let's now don't get confused by the coloring. It looks like the default colorings are a little different in these examples. This one looks close, but it has IQ on the x-axis. We need MRI on the x-axis, so let's pick this one and just take a look. Okay, so it's very hard to see. We've got these dots, but yes, indeed, they're in the right place. The colors aren't specified, but it's clear that that's the right one. So I'm going to go with choice B. Okay, so now I'm going to separately calculate the correlation coefficient for males and females. So I'm going to go to summary stats for correlation, and I'm going to still do MRI and IQ, but now I'm going to group by sex. So what I'm going to get now is two correlation coefficients, one for males and one for females. Here we go. Isn't that beautiful? So for females, the correlation coefficient 0.119. For males, negative 0.217, rounding up. So if we go back to the critical values necessary to state that there is a significant correlation between the two variables, now we have only 5 males and 5 females. For a sample size of 5, you need a correlation coefficient to be greater than 0.878 in absolute value. These are both smaller than that in absolute value, right? They're pretty close to 0, and so I would say because the correlation coefficient for females is it's positive, right? And the absolute value of this correlation coefficient is 0.119. I'm still taking 3 decimal places. Is not greater than, what was that number again? Let's pull up the table. For a sample size of 5, 0.878. Okay, 0.878. It's not greater than 0.878. No relation exists between MRI count and IQ for females, because the correlation coefficient for males is negative, and the absolute value of this correlation coefficient is, let's type it in, absolute value, I leave off the negative sign, 217. This is, again, not greater than the critical value for the male data set. And again, because the sample size is 5 for males and for females, 878. And I'm going to say no relation exists between MRI count and IQ for males. Great. All right, now we have an idea about what correlation is. We're going to look at finding a line that's going to be a good predicting line. what we call a line of best fit, or a least squares regression line. It's called least squares regression line because this is a line which, if you were to take the difference between what the actual points are and what the predicted points are, all of those differences, square the differences, they're called residuals, square the residuals, and add them all up, there's one line that's going to achieve the task of minimizing the sum of the squares. Okay, so that's very wordy, but we'll call it a least squares regression line. Don't worry about exactly how it's calculated for now. It's very easy to do in StatCrunch, and that's what I'm here to show you. So we're going to, again, open in StatCrunch, open this data in StatCrunch, and I'll show you how quick it is to do linear regression. So we have, all right, so we've got, let's move this. I always like to move it. I'm going to, I have my data, my X and my Y data, great. I'm going to go to Stat and down to Regression. A simple linear regression is where we have just X variables and Y variables. We will look at more complicated regression later. Here, my X variable is X, big surprise. My Y variable is Y. All right, now I'm going to include in here, let's see, a fitted line plot. Okay, I'm going to include that line plot. That's going to be in the output. That's a standard output. Let's click Compute. So now my output window has, let's make it a little bigger so I can see everything. My output window includes a lot of stuff that we're not going to look at right now. Right now, the main thing we're looking at is the equation for the line, which is given right here in the fourth line of output. That gives me an intercept and a slope. Now, be careful. Be careful because the intercept is the first term here, and the slope term comes next. Here, my output is reversed, so I'm going to do it the other way. So it's the negative 0.674 is the first. So negative 0.674x plus 6.582. I have to round up. Okay, so just be sure you're putting these in the right places. Okay, now the next piece of this is to what does the graph look like for the least squares line. This, notice on my stat output I've got 1 of 2. If I click this little right button, I actually get the line of best fit. Let's scale this so that it looks closer to what we have here. So this is the picture I want to have, and just looking at it, I can see that we have these 3 points below and 3 points above. So this is the kind of the picture I want to look for. It looks close to C. Let's look close up and see if that's it. Yeah, that looks good. I'm going to go with C. We have these 3 points above, these 3 points below. That looks great. I think so now I've got some data. We've got a data set, and we're going to go and do some more linear regression stuff. So let's open this data, look at the table. Okay, very simple. We just have 5 data points. Let's open StatCrunch. We want to avoid doing any calculation on our own. So that's my goal here, is to show you how to do all of this stuff without lifting up a finger to write with pencil on paper, because we can use the software to do almost all of that. There's once in a while we may have to do a little bit of a calculation, but we're going to try to avoid it. Okay, so we're going to do what we did just now. We're going to go to Stat. We're going to go to Regression, a simple linear regression. Once again, we'll pick X for our X variable, Y for our Y variable. Click Compute, and we'll get our statistical output again. Let's open it up and see what we got. Okay, so you can see we've got Y is 1.6 plus 1.9x. Now this is reversed, but we just have to look for the right one. It's 1.9x plus 1.6. That's perfect. Graph the least squares regression line. Again, remember that's right here in the output. I'm going to just make it square so it looks a little bit better. Tries to match this. I'm going to match the axes just so it get a really clear picture. I have x going from -3 to 3, and it looks like for all of these y goes from -6. Oops. Looks like y is going from -6 to 6. So I'm going to go -6 to 6. Okay, well, you have to just try to ignore the axes and where they cross, but the main thing is to look at the line and see the dots going above and below. It looks like C. I'm going to open up C and see if it's close. I can see this point's a little bit above. That one's a little bit more below. That's kind of medium above, and below. C looks good. That's what you have to look for. It's really the line that looks like it follows the pattern of it the best. Okay, what's the sum of the squared residuals? Now, if I go back to my statistical output, it gives me a lot of other stuff. I said I'd look at it later. Let's look at some of it now. If I scroll down, I have analysis of variance. This gives me a lot of information which we will look at in more detail in a later module. But for now, you should know this row for the error. Errors are kind of another word for talking about residuals. The error is the difference between what is, I'll show you, what is predicted by our model and what is plotted in our data, okay? So that is how much error our model has with respect to the actual data. So each of those differences could be thought of as a little tiny error, all right? You could take all those errors, if you square them all and you add them up, that's the sum of squares. And that is right here, this when we say SS, that stands for sum of squares. So sum of squares for the errors is 1.1, and that's it. And that's all it was asking for. Okay, new problem. We've got an engineer who wants to determine how the weight of a car affects gas mileage. The following data represents weights of various cars and their miles per gallon. Okay, so let's open this in StatCrunch. First thing we're going to do, just as before, is we're going to find the linear, the least squares regression line. So that'll be the first task. And what is going to be involved in that is the exact same procedure. We just go to the regression menu. Okay, I'm going to again move it. Go to Stat. Regression, simple linear. Now, this time we're going to determine how the weight of the car is X. Oh, it's labeled with X right there. That's great. The miles per gallon, Y. Okay, let's click compute and just see what we get. The least squares regression line is given to us. So we've got our intercept and our slope. The slope is -0.0039, rounds up to 4. And then the intercept is this 34.2045. I again have to round it up. Okay, great. We're going to now do a little bit of interpretation. What is the slope and intercept? So the slope is, since the weight of the car is pounds, the slope is saying, okay, if we increase the pounds of the weight of the car by a single pound, we expect on average that the miles per gallon will decrease by 0.004 miles per gallon. So the slope indicates the mean change or average change in miles per gallon for an increase in 1 pound in weight. That's the interpretation we give for the slope. The best interpretation for the y-intercept, it doesn't, so if x equals 0, then the miles per gallon would be the y-intercept, 34.2044. But what does that mean? A car that weighs 0 pounds? That's not realistic. In some problems, the y-intercept has a realistic interpretation. Sometimes it doesn't. This is a situation where it's not appropriate to interpret the y-intercept. It doesn't make sense to talk about a car that weighs 0 pounds. Okay, now let's talk about prediction. To do a prediction, we can actually just plug numbers into a calculator, but I'm going to show you how you can do it in StatCrunch. So let's go back over to our stat output and hit edit. Here I'm going to scroll down a little bit. A prediction value of y, I'm going to click here and type in a prediction, an x value. So let's predict the miles per gallon of a car B. For car B, we had 3095, and what I'm going to do is see what the predicted value would be. So I'm going to click compute. And in my statistical output now, there's going to be a little bit extra, which is right down here. You can see for an x value of 3095, the predicted value of y would be 21.87817. That's great. So I'm going to put it just into 2 decimal places. 21.887 would be 88 rounded up because of that 878. So now the residual. The residual is the actual value minus the predicted value. But you know what? I'm too lazy to calculate residuals myself. Click edit again, and I'm going to go scroll down in this, and there's an option down below for me to save residuals. I'm going to, oh, and even model estimates. That's even faster. Model estimates and residuals. I'm going to click compute. I'll show you both of those things. Oh, model estimates, predicted values, and residuals. Look at that. Isn't that cute? If you look here now for car A, it tells you what the residual is. It tells you the predicted value. For car B, the residual, the predicted value. It gives you all of those. So actually, we're looking at car B, the residual, and the predicted value. I could have done that right away, but that's all right. The residual for car B is negative 1.178, rounds up to 1.8. So since the residual is negative, you can even see that from the graph. For car B, which is the, it's hard to tell because these aren't labeled, but they are in increasing order. So car B is the second dot. It is below the line. That means that this car is below average for its miles per gallon. At least as far as this model is concerned, it's below average. A negative residual means below average. Okay. Oh, and look at that part. The last part of the problem is asking us to do the least squares regression line, which I happen to already have pulled up. So, and label the residuals. Oh, it looks like it's, just looking at the graph, I'm going to magnify here. I think this is it. This looks like, you can see the points are all scattered around. This is point car B, this is what was predicted. This red line, that distance, in fact, the difference, it's negative, is the residual. So that is, yep, that's certainly our answer. Great. All right, so the accompanying data represents the weights of various cars and their gas mileage in the city. The linear correlation coefficient between the weight of the cars and its miles per gallon is this, R, negative 0.972. Okay, the least squares regression line treating weight as explanatory and miles per gallon as response is this. Okay, great. What proportion of the variability in miles per gallon is explained by the relation between weight of the car and the miles per gallon? Okay, you know what I'm going to do? I'm actually going to, just for argument's sake, I'm going to once again pull all of this data into StatCrunch, and I'm going to talk about the statistical output in greater detail and show you how to answer this question from the statistical output. It's actually a pretty easy question to answer from what the information that's given, but I'll I'll get to that after I go through StatCrunch. So, okay. Quickly, let's do stat. We're going to do not simple linear regression. We've got weight. We're predicting miles per gallon. Let's compute. Okay, some more of the output that we haven't talked about yet. Up here, now you notice that we are given that we're told the sample size and the correlation coefficient, which matches what we're told in the problem. We're told it was 0.972, which is this 0.9719. Then we have this r square. R-SQ stands for r squared. It is precisely this correlation coefficient squared. If I were to take a calculator and take 0.97190,187 and square it, I'm going to get, oh, it doesn't square the negative. I have to put it in parentheses. But anyway, yeah, it should be positive because it's squared. I forgot that I need to put parentheses around. But yeah, so we'll have 0.944, 5932, etc. That's all r squared is. You take the correlation coefficient, you square it. But r squared has a nice interpretation, which is that's the proportion of the variability of our y variable, which is explained by the model. In particular, it's explained by weight. So we can just take that r squared, we turned it into a percentage. It's going to be 94.45, rounds up to 94.5. That's what percent of variability of car miles per gallon is explained by weight. Now, let's make a residual plot. What I'm going to do to make a residual plot, go back to Options, Edit. I have some other options down here. I have residuals versus x values as an additional graph that I can create. I'm going to select that and click Compute. It's going to create, if I scroll over to the right, these are the residuals. It's the residual plot. Okay, residual plot for each of the data values. It's going to give you, remember whether that residual is positive or negative. So here's my residual scatter plot, plotting residuals against weight. And you can see this picture matches with choice B. Let's zoom in and just take a closer look. We don't have this dotted line going across at 0, but if you imagine it there, you can see that we have all of these residuals in the exact same place. I'm going to say OK, choose B, and move on with my life. Let's interpret the coefficient of determination. Okay, well, let's see. Let's go back to our data. Once again, the coefficient of determination, that's r squared. That's another word for r squared. So it's 94.5. 94.5% of the variance in our y variable, which is gas mileage, is explained by the linear model. So I'm going to look for the choice explained. Explained by the linear model. The least squares regression model appears to be what? Appropriate based on residual plot. Why would I choose that? The residual plot looks like just some random cluster of points. That's what you want in a residual plot. If you have a discernible pattern, if you have like a swooping curve, or if it looks like a megaphone or something like that, then that means that something fishy is going on and a linear model isn't appropriate. But if you just have a random scattering of points all around with no real pattern, just looks like a cloud of points, then that means that your residuals, they support the linear model. We'll talk a little bit about that in a later module, but for now you should know if there's no discernible pattern in your residuals, then that means your linear model is probably appropriate. Great.